Hi everyone. Today we're going to study optimization. In this video, we're going to see to maximize the area of rectangle. One common application of calculus is calculating the minimum or maximum value of a function. For example, companies often want to minimize production costs or maximize revenue. In manufacturing, it is often desirable to minimize the amount of material used to package a product with a certain volume. The basic idea of optimization is the same. We have a particular quantity that we are interested in maximizing or minimizing. However, we also have some auxiliary conditions that need to be satisfied. Here, we are interested in maximizing the area of a rectangular garden. Certainly, if we keep making the side lengths of the garden larger, the area will continue to become larger. Here now is the problem-solving strategy of optimization problems. We have 6 general steps. Step 1. Introduce all variables. If applicable, draw a figure and label all variables. Second, determine which quantity is to be maximized or minimized, and for what range of values of the other variables, if this can be determined at this time. Step 3. Write a formula for the quantity to be maximized or minimized in terms of the variables. This formula may involve more than one variable. Step 4. Write any equations relating the independent variables in the formula from step 3. Use these equations to write the quantity to be maximized or minimized as a function of one variable. Step 5. Identify the domain of consideration for the function in step 4, based on the physical problem to be solved. Step 6. Locate the maximum or minimum value of the function from step 4. This step typically involves looking for critical points and evaluating a function at endpoints. This is now our sample problem. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? For our solution, first, let us draw the problem and label it. Here is our drawing. On this side is the rock wall. Then we label this side to be X, and this side is also X, while the side here will be Y. Based on the problem, we want to get the dimensions of maximum area. So let us maximize the area of the rectangle. Our formula for area of rectangle is length times width. Considering the variables here, we write A equals x times y. We regard this now as equation 1. Next, we're going to write formula for constraints. In the problem, we're going to place wire fencing of 100 feet on three sides of rectangle. So we write here 2x plus y equals 100. So this equation is regarded as equation 2. Going back to equation 1, we can see that there are two variables on the right side. Our goal now is to make this formula of area in terms of one variable. So what we're going to do is to manipulate the equation 2 such that it becomes y equals 100 minus 2x. We isolated the y. And from here, we will substitute this y in terms of the variable x in the equation 1. So the area formula will be A equals x times y, but the y becomes 100 minus 2x. Simplifying the right side, we have now 100x minus 2x squared. We have now the right side of equation 1 to be in terms of x only. Now we are ready to take derivative. So the a here becomes a prime equals 100x is now 100 minus the derivative of 2x squared is 4x. From here, let us set a prime equals to 0 and let us solve for x. So it becomes like this. Solving for x, let us transpose negative 4x on the left side. It becomes positive 4x equals 100. We want the value of x. Let us divide this equation by 4. So the x now becomes 25. Now let us solve for the value of y using this formula. Let us substitute the value of x as 25 in here. So we have now y equals 100 minus 2 times 25. 2 times 25 is 50. So 100 minus 50 equals 50. So the value of x is 25 while the value of y is 50. We do not forget the unit of measurement, that is feet. These are the dimensions. Now, let us find the maximum area. Let us substitute the values of x and y on the formula 1. So we have a equals 25 times 50, and this is equal to 1250. The unit of measurement is square feet. This is the maximum area. These are now the final answers. Today, we're going to study optimization. In this video, we are going to maximize the volume of a box. This is the sample problem. An open-top box is to be made from a 24 inches by 36 inches piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. What size of square should be cut out of each corner to get a box with the maximum volume. First, let us draw the cardboard. Here is the 24 inches side, while this side is 36 inches. For step 1, we let x be the side length of the square to be removed from each corner. Then the remaining 4 flaps can be folded up to form an open top box. Just like this. Let capital V be the volume of the resulting box. Step 2. We are trying to maximize the volume of a box. Therefore, the problem is to maximize V. Step 3. Let us write the formula of the volume of a box. V, or the volume, equals length times width times height. Now, let us label our box. The height here is the x. In this side of the box will be 24 minus 2x inches. And this side here will be the length, and this will be 36 minus 2x inches. For step 4, let us write the formula of the volume with respect to our labels here. So the length will be 36 minus 2x times the width, which is 24 minus 2x, times the height, and that is x. Let us simplify this, and we will get 4x cubed minus 120x squared plus 864x. The step 5 is we take derivative of this function. After that, we will set v prime equals 0, and then we will solve for x. The v prime of x equals 12x squared minus 240x plus 864. Next, we set this to be 0, and it becomes like this now. Let us now solve for x. First, let us simplify this equation by dividing by 12. So we will have the simplified one to be x squared minus 20x plus 72 equals 0. Let us use quadratic formula. So the value of x now equals negative of negative 20 plus or minus the big square root here of the square of negative 20 minus 4 times 1 times 72 all over 2 times 1. When we simplify this, we will get the value of x to be 10 plus or minus 2 square root of 7. Let us separate the plus or minus, then we will get the two values of x. First is the 10 plus 2 square root of 7. The second is 10 minus 2 square root of 7. Let us analyze each value. Let's start with this 10 plus 2 square root of 7. When we substitute this 10 plus 2 square root of 7 to this side of the box, we will see that we will get a negative value. It means this value of x is not acceptable. So we have this value of x, 10 minus 2 square root of 7, to be the accepted one. Then we will write the unit of measurement, the inches. This is now the final answer. This is the side of the square in here. If we're curious about the maximum volume with the formula earlier about the volume of the box, let us substitute this value 10 minus 2 square root of 7 for all the x that we see on the right side. So it will be like this. When we simplify this, we will get the answer as 640 plus 448 square root of 7. And this is equivalent to 1825. And the unit of measurement, cubic inches. Today we're going to study optimization. In this video, we are going to minimize travel time. This is the sample problem. An island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying at a cabin on the shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? We put an illustration here for better understanding of the problem. The island is here. It is due north from the straight shoreline. The cabin is here, which is 6 miles from this point. So for step 1, we let x be the distance running and let y be the distance swimming. This is the x from here up to here and the y from here up to the island. Let capital T be the time it takes to get from the cabin to the island. Step 2, we identify that the problem is to minimize capital T, or time. Step 3, to find the time spent traveling from the cabin to the island, add the time spent running and the time spent swimming. Since the formula of distance equals rate times time, or we write capital D equals capital R times capital T. We write here that the time spent running is capital T sub running equals D over R. D sub running over R sub running. So the value here is x for the D over 8. This is given in the problem as the 8 miles per hour. So x over 8. While the time spent for swimming is capital T sub swimming equals D over R. D sub swimming over R sub swimming. And the value here would be y over 3. This 3 here is given from the problem, which is the rate of swimming, and that is 3 miles per hour. Therefore, the total time spent traveling is T subtotal equals x over 8 plus y over 3. We regard this as equation 1. Step 4, looking at our figure here, the line segment of y miles forms the hypotenuse of a right triangle with legs of length 2 miles and the quantity 6 minus x miles. Here is our right triangle. Therefore, by Pythagorean theorem, we can write 2 square plus the square of the quantity 6 minus x equals y squared. Simplifying this, we can get the value of y, and that is y equals the square root of the square of 6 minus x and then plus 4. This equation here we regard now as equation 2. We need this value of y in terms of x that we need to substitute in equation 1. So the equation 1 now becomes like this. T of x equals x over 8 plus the y here now becomes this big radical, and we write it here, all over 3. Step 5. From the figure here, we can see that x must be between 0 and 6. Therefore, the closed interval 0, 6 is the domain of consideration. Now step 6. We're going to differentiate the function, the t of x. And then we're going to set this t prime of x into 0, and from there we will solve for x. So we write again step 6 in here, and then we write the function t of x. Let us now do differentiation. T prime of x will be equal to the derivative of x over 8 is 1 over 8 plus the derivative of this will be the constant 1 over 3 times 1/2 times the radicand here will be raised to negative 1/2 times the derivative of the radicand will be 2 times the quantity 6 minus x times the derivative of negative x is negative 1. Now, let us simplify this big expression here. Also, let us set t prime of x into 0. So we will have this 0 equals 1 over 8 minus 6 minus x all over 3 times the big radical here. From here, let us now solve for x. Let us transpose the second fraction on the left side. So this negative becomes positive. And from here, let us do cross multiplication. So our new equation now becomes 8 times 6 minus x equals, this whole radical will be on the right side. Then let us square both sides so that this radical will be cancelled. We have now 64 times the square of the quantity 6 minus x equals 3 square will be 9, and this radical here will now be removed. When we multiply the 9 into the terms inside the grouping symbol and simplify by combining similar terms, we will get this 55 times the square of 6 minus x equals 36. Let us divide both sides by 55. So we will get 36 over 55 on the right side, while the left side will be square of the quantity 6 minus x. Let us take the square root of this equation and then we will solve for x. The value now becomes x equals 6 plus or minus 6 over the square root of 55. We can see that we have two values of x. To separate them, we write x sub 1 equals 6 plus 6 over square root of 55. The second value is x sub 2 equals 6 minus 6 over square root of 55. If we analyze x sub 1 and we consider step number 5, we can see that this x sub 1 value is out of the domain. because our domain is from 0 to 6 only. It means this value x sub 1 is not accepted. The x sub 2 value is the accepted one. Now, to justify that the time is minimized for this value of x, we just need to check the values of the function capital T of x at the endpoints, that is x equals 0 and x equals 6, and compare them with the value of the function T of x at the critical point x equals 6 minus 6 over the square root of 55. This is the value that we derive here. We write again this function. So we start with a t sub 0 and we will get 2.108 hours. For the t of 6, we will get 1.417 hours. While for the t of 6 minus 6 over the square root of 55, this will give us 1.368 hours. So we will get the smallest time here. This value can be simplified into 5.19, and of course we don't forget the unit of measurement, miles. This is now the final answer. I hope you learned something from this video. See you again next time.